we can do maybe another example, something maybe more for defining vortex forces or stuff like that. So that's quite fun as well. And we can do that with rigid body dynamics, or we could do that with particles as well, because the rigid body dynamics, especially if they're packed, they're basically a bunch of points and they're going to be particles anyway. So maybe let's build ourselves a custom velocity field using these cross product vectors. So how does that work? Well, let's first start with thinking about, I need to scatter some points, and we're going to define eventually sort of a field, right, an area. So let's maybe we can eventually also let's do it actually in the ZY plane, so that we can scatter a bunch of points on there, and then later on use that to duplicate that along a line. So we'll see where this goes. So first of all, I want to scatter some points onto this surface, and again, we'll need some normals onto this, because currently, oops, this does not have any normals. So if we say here, let's create some normals, and actually we can maybe specify them ourselves, because I think the normals over here are going to be computed in a way, well, maybe this is useful, we'll see. Let's have a quick look. If we put this 2 points, all right, this will, yeah, we can use these normals. The other normal that I want is the one that is pointing away from the center. So that means every single one of these points over here, right, is basically flat in the plane and has a certain, you know, position away from that center. So if we were to say, okay, go and compute with an attribute VOP, we can go and compute the normal based off of the position of each of these points. So here, a normal that is basically based off of the position. So it is going to point away from the center. So all of these normals, right, it's a little hard to see maybe. So let's scale the normals down a little bit so we can kind of see a little bit better. 0.01 should do. Right, so here we can kind of start to see, okay, all of these normals are now pointing away from the center. Also, just doesn't need to, but just to be clean about it, we can give this maybe just some more division, so it's kind of nice and smooth around the edges. I don't really necessarily want the faceted look. Okay, so with this, the next thing that we can do is compute the cross product. So here, we can either do that in one go, or we can, you know, merge and blend them together. So that means the thinking in just a moment, right, is I want to create some kind of a vortex force. But where do we want the vortex to happen, right? Do we want the vortex to happen on the outside, in the middle, or on the inside? So we can start blending different vectors together. So we can kind of do that in just a moment. So if we were to say, okay, if I take this normal, which is pointing from the center to the outside edge, and I combine that with this other normal, which is literally pointing forward, right, or in one of these axes. Actually, let me double check for a moment, because this is still not right in the right axis. So it should be the XY plane, actually, the XY plane. Yeah, and the reason for that is if I were to create some kind of line segment, so we can do this briefly by dropping down some points here, and I'm going to transform these points. So now I'm going to create the backbone, if you will, for each of these curve forces that I'm about to define. So if we say, okay, you can kind of go here, maybe a little bit further, something like this, and one more, maybe, sure, somewhere over here. So if we merge these points together, we're going to be able to create a little polygonal line segment out of that. And with that polygon line segment, with an add operation, we can basically turn that into a NURBS curve in just a moment, right? So here by group. So now we have a nice little polygon line segment, and we can convert this segment to a NURBS curve. And so then we can resample the NURBS curve again. So here, output that to a NURBS curve. We can resample that again, all right? With that, we can compute the tangent normals now. So we can use a polyframe for that. So the polyframe allows us to go and grab those tangent normals. So, okay, I actually don't want the normal, I want the tangent. So we can just, I don't know, either turn it off or I don't really care. I'm going to turn this into N, my normal. An up vector might be useful. So the bitangent might be useful. So here, if we say up, right, then we can kind of see if we bypass and reevaluate. Actually, the vectors are there, and the up vector should be there as well. Let's see what happened to the up vector. We'll have to see if the up vector came through properly or not. There is an up vector there. I don't know why it's not necessarily displaying. Oops, there we go. All right, so there's the up vector. So why does the up vector look huge and the other one looks so small? Well, that's simply because of the display in the viewport. So we've got scale normal and scale vector. So here we see scale normal, and here this will be scale vector. So if we set this one to 0.1, they'll basically be more representative. The other thing is we probably have a bit too many points right now. So we'll see, maybe we can set this to like 0.3, all right? And we don't really care now anymore about the line segment. So I can literally get rid of any of the geometry and keep the points, right? So now we can kind of see that we have the geometry, right, as points, and each of those has got a tiny little coordinate system. This is our normal and our vector, which we need for scattering. So what are we going to copy onto there? So here, copy 2 points. Well, we basically can copy our little circle on there. So when this goes through, right, we can kind of sort of see right now that it basically is creating all of these circle segments. We don't really care about this. We can visualize the normals, right? And we're starting to create sort of a point cloud with normals on there, right? But a point cloud with normals, eventually, if we wanted to, we could do a rasterization operation. So let's see, attribute rasterize, I believe it's called rasterize, volume rasterize attributes, I think it's this one. Yeah, and this one will allow me to grab some attribute. So let's see which attributes we want. We want the normal, which eventually will become the velocity attribute. So I'm going to turn this as a V, as a velocity attribute. Currently it's looking for density. There is no density. We'll deal with that in just a moment. We haven't used the cross product yet. Where are we going to use the cross product? Well, we are going to use the cross product to define here rotational vectors. So maybe let's dive back before we start building our volumes. We should first define our vectors properly. All right, so let's do the cross product. Also, maybe not a bad idea is to simply save the scene again. Right, there we go. And so the cross product between what, right? Between the incoming vector over here, the forward-facing vector, right? And between the normal that is pointing away from the center. So the incoming normal over here, right? We can use that one. And we can also use the other one, and we can normalize the result, and we're going to see that we're going to get these sort of rotational vectors, right? So here we can kind of see as we plug that in, right, we're getting this sort of rotational system. So if you need to do swirls, if you need to be big tornado, or you know, something, and this could be for flip fluids as well, something that rotates around, you can create a nice vortex force this way if you wanted to. But the cool thing is you now have control over it. Well, where do you want to do what with these vortices, right? Do you want to kind of rotate it everywhere, or maybe on the outside we might want to blend a little bit inwards? So if we were to start mixing some of these normals together, we can say, well, on the outside I want you to actually point inwards. Right, so that's kind of like a containment field. Basically, this, you have to start thinking of this as a force. If there's a bunch of particles or a bunch of fluid here, and it's basically going to rotate around, right, then we want to make sure that the particles on the outside actually are contained maybe within this field. So how do we do that? Well, we can kind of reverse the incoming, negate the direction of this incoming normal. And we can also use where we want this specific vector to be active. So if we say, actually, I want you to blend, and we can use the distance, so we can use the length, and we're dealing with a unit length circle right now. So we can kind of say over here, as we go from 0 to 1, as the radius increases 0 to 1, we can map different forces or different directions along this distance, right? So we can do that. All right, so let's go grab the position. There's my length, and we can link that in with a ramp, and the ramp is basically the weight of each of these different vectors. So we can eventually either use a mix, or we can do 3 and do fuzzy logic and blend them together. So maybe let's do that. So here, the first one that I'm after is maybe the containment ramp. And so the containment ramp is going to be, okay, where do we want the vectors to be pointing inwards? So pointing inwards, if we look at this, right, pointing inwards, I negate it, and we have the simple outgoing vector. When we negate that, right, that's going to become the ingoing vector. And so if we multiply this vector, right, together, and we say, okay, I want a little bit of this vector, and already you can kind of see my ramp here, my default is kind of affecting where this force is taking place. So there's more containment happening on the outside. So if we were to go up and start playing with this a little bit, then we can kind of see, okay, I want a lot of containment force on the outside. So maybe we can just set this to a full value of 1, and then not so much containment to the inside. So maybe, you know, something along these lines. So that means any kind of particle that starts to come to the outside edge is actually going to be pushed back to the inside. And really here on the inside, that's kind of where whatever behavior we want is going to happen. So the behavior that we want is probably a rotation. Okay, cool. Let's introduce the other behaviors. So what is one of the other behaviors? Well, instead of containment, we might want to say this will be my vortex. So where do I want the vortex to happen? My vortex ramp. It'll be probably somewhere in the middle, right? So because in not the very center, but sort of the range in the middle. So let's do that next. So I can now say, okay, let's grab our cross product result. So here, this cross product resulting vector right here, this one. And we can simply say, go grab this vector and multiply it by our vortex ramp, right? And now how do we combine these two? Well, we can simply add them together. And that's basically what fuzzy logic allows you to do, right? So we can add a little bit of containment with a little bit of rotation. Now, currently the rotation and the vortex ramp, because I duplicated it, are pretty much the same, and I don't want that. I basically want to modify this so that we say, actually, you know what? I don't really want to do a lot of rotation on the outside. So here on the outside, we can lower that. So you can kind of see the area where it is going to rotate. I'm changing. And instead, I want to have heavy rotation on the inside here, and maybe at the very center, right? I mean, we can let this fall off. It's okay, right? But at the very center, I don't necessarily need to have a lot of rotation. Instead, at the center, we might want to have a little bit of, you know, force, right? That is going to push the particles forward. So let's go and figure out which force is that going to be. Well, that's the same one that we already had over here from our normals, from our scatter, that is going to push the particles forward. Now, I may still need to flip that around so that it's pushing it forward in the z-axis. Depends a little bit because over here, my polyframe has created normals that are actually pointing in the other direction. So generally what I like doing is I would end up double negating my normal right now, which I don't want to do. So I will fix this normal, and I will also fix the other one so that it is actually pointing in the positive z-axis. So that makes more sense in my mind. Okay, so then vortex ramp. So that will be, what shall we call this? This could be, I don't know, the actual force, the sort of forward force. So I don't know, let's make this actual ramp, just because that way, when we're dealing with some of Houdini's force subs, it'll be named in somewhat of a similar way, except maybe for the containment. That, I don't know, that's just something I just came up with now. So the actual ramp, which one is that? Well, that is our normal as it is facing forward. So if we just double check that indeed it is the one, right? It's not really facing forward, it's facing backwards. So I gotta negate that vector as well. Negate. And let's go grab that normal over here, and we're going to shove it into our negate. And we're going to again multiply that with our ramp. So here our vector goes first, and then our scalar value from our ramp goes in there. And then we can simply add that in with everything else. Notice that currently I don't want to normalize the values after the multiply. The whole point is to be able to weight them using these various ramps. So we have here the first one, the containment ramp, then we have the vortex ramp, and then finally we have the actual ramp. So actual force will be the one that is going to point forward there. Okay, so let's grab the resulting output here and shove that into. So now we can kind of see that already some of these vectors are no longer flat in the plane, but instead are pointing forwards. So let's play with our ramp a little bit. And so where do I want the value to face forward? Well, especially in the middle, right? So over here we want to say, okay, this is the middle. So especially here, and maybe not so much on the outside, right? So that means on the outside, you're gonna need to be contained, right? And so you can kind of see, maybe it's even more obvious as we kind of scale up our normal a little bit, right? There we go. So now you can really see that, okay, on the outside, it's pushing inwards, and then in the middle side, it is pushing it forward. Cool. So this could be a nice way to define your forces. Now, obviously, as we kind of start playing with this, we might want to, modify these a little bit more. Okay, so basically, next up, we want to sort of, maybe we need to tweak this a little bit in terms of the containment or the vortex ramp or stuff like that. But I now want to sort of see what happens as we copy this onto the points, right? So here, I mean, it's basically a point cloud with all of these segments, right? And we can sample all of these points and we can resample if we need it, but let's basically look at the normals. So as I was saying, right, these are pointing backwards. Why is that? Because our template points are pointing backwards. So here, if we look at these normals, the polyframe tends to do that, right? Basically computes that. So all I need to do is, I believe in a normal, we can reverse the normal here, reverse the normal. I don't actually want to compute it, and simply plug that in there. Okay, so now if we look at these points again, all of it is sort of, containing, rotating, and pushing forward. Great. So we can either use these points as they are and in the subsolver or in a particle system, use them to advect, or we can use over here a velocity attribute. So that would mean we're going to rename. So I'm going to do an attribute rename and simply rename my normal to V. So that means right now we can no longer see it in the normal, but we'll be able to see it as the velocity. So there are tiny little velocity vectors on here, a little hard to spot. So let's open that up. Velocity is again a vector, not a normal. So that means if we modify it, and also just so you know, this is a trailing vector. So what does that mean? Well, the difference is if you have any kind of marker or any kind of guide over here, for instance, let's just pick the cross product, for instance, you can kind of see that it currently says style vector versus vector trail. So vector means it's pointing forward, whereas a vector trail means it is, at least for the display purposes, it is trailing behind, right? But basically the values underneath it are exactly the same. All right, so volume rasterize attributes now, we have a velocity field over here, and so we should have a velocity field in here as well. Right, so if I turn on my hulls, we can kind of see the entire container over here, the volume that has just been created, a VDB, a velocity field, and we can now use that velocity field. Now if I press W, right, and we can kind of see the volume velocity field, right? So why does it look this way, right? Why is it over here visible and here invisible? Well, that's because over here these values are pointing in negative directions, and Houdini can't display negative voxel values, it just sets it to 0. So that's basically why it's over here it's visible and here it is invisible. Now, if we wanted to sort of briefly see if this is actually working, we could also create a density attribute on these points. So let's do a quick, we can do an attribute create or an attribute wrangle, doesn't matter. Let's do a quick density attribute. Now let's set that to 1. Cool. Up. So now I should have a density volume. The reason why is because if I wanted to visualize in the viewport, right? So now we can kind of see if this looks a little weird and this looks good. Why is that? Well, basically this is the density and this is also the velocity. So generally people tend to hide their velocity volume using a primitive, go to volumes, adjust the visualization, set it to invisible, and specifically do that for the velocity. So we don't actually see the velocity field. So now I'm literally just looking at the density field. Okay, so that's kind of useful because now we can split them out again, scatter some points in the density field, use a volume trail operation to sort of see some of these points. So okay, let's scatter and let's blast everything except for the density field. So here delete non-selected, bunch of points, right? And so now I have a bunch of points scattered in the density volume. Why do I want to do that? Because I want to visualize using a volume trail operation. I want to visualize my velocity field. So here we're currently blasting everything, right, except for the density field. Well, let's blast everything except for the velocity field, right? So here I could have delete non-selected too, but yeah, if I have more volumes eventually. So there is actually a velocity field here. And so if we feed that as the second input, we can now see these scattered points, right, are basically going to create streamers. Right, so just like what in DOPS is doing, and we can basically see what the kind of velocity field is going to be. So it's a nice way to be able to pre-visualize that, right? So that's cool. All right, so next, let's dive into DOPs, make some particles, and see if they advect along this with this volume field, right? So again, cool way to use a cross product to generate this sort of very controllable tornado thing. The other thing that we haven't really done with this is if you wanted to, you could add other attributes such as p-scale and other things onto your, onto your outline points, right, onto these points. So that basically means you now start to control the radius of the tornado or whatever along the curve. This can all be animated as well, and so on. So fun stuff, and really nice that you are able to pre-visualize it where your containment field turns into sort of rotational tangential force. Okay, let's save this as well. Okay, so in this section, we're going to add a little bit of DOPs, a little bit of particles, and maybe have them advect along this. So the first thing I want to do is create a source object. So this will be my source sphere, right? And we can either scatter on the surface, or we can convert VDB to polygons and scatter in the volume. So we can do that too. So VDB from polygons. Here, I want some polygons. I'm gonna crank this up. Let's make it a little smaller because we do want to kind of stay within our forces, right? So that we have enough. And then this shouldn't be a surface, it should be a fog SDF. I want to fill the interior detail here. Let's give it a little bit more voxel, say 0.01 instead. And let's scatter some points in there, which will become the source of my particle system. Okay, so now this will become the source of my particle system. We don't really want to do the relaxing of the iterations, and I also want to modify the seed based off of something like $FF so that it changes over time as we start emitting. Great, so now we can say go create a DOP network, and inside here we can make our particle system. So there'll be a pop object first, pop object. Where's my pop object? There we go. We also want a solver, so that's our pop solver. Hook them up. And then we need to source in there. So again, a pop source. So I want to use from the first incoming geometry here, we're going to use that. The second incoming geometry, I eventually want to use my volume trail operation. And so now we can kind of say, all right, go and source from the all points from the first context, right? And let's have a quick look as this plays back. It should start emitting points. That's good, quite a lot of them. We can make them live for, maybe a little shorter, I don't know, maybe 10 frames or 5 frames, so it doesn't live too long. Maybe some variance as well. And then finally, let's bring in that force. So here we can just do pop advect by volume, just like what we did when we did the advect curve, right? So here pop advect by volumes. And which volume do we want to use? Well, we can use now that second input. So here, second context geometry, right? That is coming from here, the second, oops, that's the visualization. I actually want the volume. Now, the one thing to note, right, is that, so here we have our VDB volume that is coming in. It is named currently V. So that is the one thing that you should pay attention to, because here inside of our .NET, this pop advect defaults to val. So just make sure you set that to V, it'll be fine. And then update force, do you want it as a force or do you want to update the velocity? Well, I'll just set this to velocity and let's see, maybe it's too strong, right? But there it goes. It's basically doing its thing and it is starting to rotate along. So now we can kind of, start playing with this. Maybe the containment field is a little bit too strong. So let's play with the force a little bit. So we can kind of just redial over here. Maybe we keep the visualization on the .NET and we simply redial the way that our original sphere over here is kind of containing, right? So currently I think it's getting a little bit pushed too much to the center. So I don't know if that's coming from the containment ramp over here, or if we, I don't know what else we can do with that to sort of play with that a little bit. But yeah, so let's see what else we have. The actual ramp. So we definitely do want to push it forward. Maybe not so much on the outside, maybe only on the inside. And then again, maybe that containment field, let's maybe make that a little bit less extreme. Currently, the reason why it's so slow is because I've templated my force over here, right? So anyway, in the vortex attributes, maybe we want to make it swirl a little bit stronger. We can also have a global multiplication onto these attributes so that we say, okay, you know what, instead of every single one of these be starting with a normalized vector, we can add an additional multiplier on there that we can kind of say, okay, the vortex ramp, I kind of want to make that one a lot stronger, right? So that we can control how much each of these scales actually is. So if we want to do that, we can simply add some parameters in there, right? And then this would be something like containment mult. So this is the global amplitude for the containment portion, right? So we don't have to stick between 0 and 1, right? Over here, notice I'm adding them up and they are no longer normalized, not necessarily. All right, so by default, we can set this to 1, set this to 10. Let's do the same thing now for the other ones. So instead of containment mult, I want to do vortex ramp. Right, so here, also again, probably a good idea to save this vortex mult. Grab this, and finally for the actual force as well, we can basically say actual mult. Alrighty. Okay, so now we have all of our different forces. So now if I wanted to say, you know what, I want it to swirl more, right? I want a stronger force when it is kind of rotating. So we can basically say, here are our different amplitudes, right? Or amplitude values. So if I were to crank up, I don't know, let's see what happens when we double our vertex or our vortex multiplication, right? So here, that means more rotation is going to start to come in. Okay, cool. Let's have a look at that. Maybe we want to do less containment. So again, if we go to our particle system now, maybe we can do a little bit less particles too. So maybe like 100 instead, and let's play that back. And so there they go. So basically they're moving along my curve and they're doing sort of their rotational kind of thing. Now currently they're doing it all at the same amount, right? We could randomize that per particle and so on, and maybe increase the amount of actual strength as well. So the actual force over here. So you say, all right, maybe let's duplicate that to 2. And now they're kind of going a little bit faster. This can be combined with other forces. So obviously if we were to combine this with a quick pop wind to add a little bit of noise into the system, right? We could do that too here. And wind velocity we don't need, right? This is going to come from our pop advect by volumes. Here we do want a little bit of amplitude, and just let's see if it's working. Right, so okay, this is starting to break things up a little bit, right? So that's cool. You know, it's no longer, you know, truly uniform, right? It's kind of fun to play with. And then you can kind of play with these settings in terms of the swirl scale and the swirl size and all that. If we set this a little bit smaller, we should get more ripping things apart. Also, our source is very uniform. So if I were to really continue with this a little bit more, I would break up my source further. Anyway, I hope this gives you some cool ideas on how to use the cross product, because it's a very powerful operation. Later on, you know, instead of just this kind of force, any kind of rotation, any kind of orientation of points and things like that, the cross product is going to be really useful for. In later classes or later tutorials, we'll talk about maybe using the gradient of the SDF and things like that, and how the cross product can use that for scattering points in the volume versus scattering points on top of an object. I hope you enjoyed this. If you liked these kind of videos, please do like and subscribe, and I look forward to making some more. All right, see you next time. Bye-bye.